Oops. It wasn't a side length of 0. Sometimes you're going to get the idea where we're going to wind up with both a 30, 60, 90 and a 45, 45, 90 triangle put together. And when that happens, it's a matter that you're going to have to pick a spot to start and then rotate it into the second triangle. So it's not that it's any more difficult than what we've been working on. It's that it just takes an extra 2 minutes to make it. What's different with these types of problems, as opposed to saying solve for all these examples, these will usually say solve for, in this case, they're saying call it x. Now, I apologize that they're using this value of this x here because I've been using it for something different. I'm just going to say, instead of mixing it up here, we're going to find that side length right there. Just call it question mark, so you don't confuse it with this x value. So when you see a problem like this, first thing you want to do is identify which side length do you know from across from what angle. So across from what angle do you know a side length? A 30, very good. Everybody see that? We know across from a 30 is equal to 10. So what I do then is I always start by writing out, okay, I know across from a 30, so I'm going to write out my 30, 60, 90 first. I know that I know across from my 30 is some, I'm looking at some value of x, and in this problem, that value of x is going to be equal to 10. Which means, everywhere else I see an x, what am I going to put? 10. So in this case, I just filled them all in just so you guys see where we're going with it. But really, I only needed to figure out one of those side lengths to be able to get me to the next triangle. Which side length did I need to figure out? I needed the 60. I needed to get to the 60 because I eventually have to find the 90 on the other triangle. But everybody see how this is a shared side between the two? So I have to figure out what the 60 is looking at, so that way I can figure out what the 45 is looking at. See where I'm going with that? So I know that across from the 60 is this value of 10 root 3. So now I change my ratios to a 45. And I rewrite. And now I know across from a 45 is equal to 10 root 3. Which now means in that triangle, everywhere I see a value of x, I'm going to rewrite it with 10 root 3. And which one of those side lengths did I need to find? Across from which one? I had to find it across from the 90 because it was this guy that had the question mark. So in my calculator, I type in 10 root 3 times root 2. Now, when you have that 2 roots there, make sure that you hit the right arrow so that we get out of the radical. And we don't accidentally multiply 2 radicals together. It's not really good. So you'd write in 10, it's not 13, 10 root 3 times root 2. And it would look literally like you just wrote it. You get 10 root 6. And it does it automatically. It's the idea that you're using both ratios to get you there.
You guys, it's a good idea while we're doing this and getting into all our pretty stuff that you actually have your calculator. That you actually have your calculator in class, so you could practice that on how you're actually multiplying these radicals, and when we get to our trig functions, the order that you're going to be pressing those buttons. It's going to be really important.
Yeah. And that's what these look like. They look weird, but as you get into them, you're just doing the same work kind of twice. Okay, go for it. Do this. In the multi-view calculator, when you did 9 divided by 2, did it just say 9 over 2? I forget if it does it that way or not. Or did it give you 4.5? Give you 4.5? Okay. I was going to write it out the same way that the calculator did it. Okay. For what? Remember, you have, right now, you've got the equation, you know across from the 90 is equal to 9. 2x equals 9. Solve for x. So then, everywhere I see an x, I'm going to put a 4.5. And I only need to worry about which value, which angle I need to worry about. The 30. The 30 gets me to the other triangle. The 30 gets me to the other triangle. Now that 30, that value of 4.5 is across from a 90 in a different triangle. It's across from a 45, 90. And once again, I have the equation, something times the square root of 2 equals 4.5. How do you undo multiply? Divide again. So in the calculator, if you divide out, remember if this one will do a decimal on this one or not, it might. And there's a reason why it's doing that, because it gave you that, yeah. The calculator itself, once the multi-view calculator switches something into a decimal, a lot of times when you start multiplying it by other radicals, it's going to just go straight to a decimal. Or dividing them. Now, on the other hand, that's why I asked you guys if it gave you the value of x was 4.5 or 9 over 2. If you used 9 over 2, it would have given you a cleaner number as far as this is concerned. No big deal. So this is that value of x, 3.18. So everywhere I see that, and there was my answer, because I needed to find the approximate 45. If you had the 9 over 2, excuse me, if I did the fraction bar of 9 over 2, I think if I wrote it this way, divided by the square root of 2. I think it would, yeah, then it would have done something like that. You might have gotten 9 root 2 over 4, depending upon how the calculator put it through. Okay. Just so you guys are aware, it really depends on how you type some stuff in with this calculator on what it will spit out. That's what we're looking at today. That's the only new stuff that I'm showing you guys for today. I don't think it's that bad. It's basically just taking one more step than what you did yesterday, or 2 days ago. We did that on Wednesday and Thursday. Right. The other thing I wanted to remind you guys of, in the past two sections, basically what we have done is this. What's that? Pythagorean theorem, isn't it? When do you use that? Finding side lengths, right? Finding side lengths of what kind of a triangle? A right triangle. Do you have to, can you use this with 45, 90s and 30, 60, 90s? You can, absolutely. It's a lot easier with the 45 than it is a 60, but you could. Now, can I use 45, 90s and 30, 60, 90s if I have a right triangle that has a 3 here, and I don't know what this is, and I know this is 7? Can I? Rephrase that, Josh. Can I use a special right triangle? Is this Is that triangle right there with a 3 and a 7 trying to find x there, is that a 30, 60, 90 or a 45, 45, 90? It's not, it's neither because it doesn't say it is. You only use these special right triangles if it is in fact a special right triangle. And it would have to be shown to you. It would have to say that both of those were the same. You would have to have a 60 here, something like along those lines. That's the only way that you would ever use those two. I just wanted to reiterate how that worked. Now, what are you solving for in this case? Are you solving for a leg or a hypotenuse? Hypotenuse. So the hypotenuse of the Pythagorean theorem is what part? C. C. What's 3 squared? What's 7 squared? So you have 9 and 49. That gives you what? 58, I believe? And how do you undo the square root? What's the square root of 58? What does it say? What is it? Yeah. So it's the square root of 58. So the calculator does not simplify that. So there's your answer. If it was simplifiable, the calculator would simplify it for you. Not every time you're going to get a radical that simplifies, like a 3 root 6 or something along those lines. It doesn't always have to happen. What was different if you had that? Yeah, that value of x now is moved to become a leg, and you just have to do one extra step. You'd have x squared plus 3 squared equals 13 squared. So this is the actual equation and that you'd have to do a 2-step with. Subtract the 9 and then take the square root. If I did that, what's that? 16 and 10, so 4 root 10. I think that would simplify out to me. You have 4 root 10 and one like that. All right. Very easy. Nothing too crazy. Now, the other thing that you did with the Pythagorean theorem, if you remember, it was either you could tell whether or not it was a right triangle, a acute triangle, or obtuse triangle. And when we did that, we wrote the C value first. So if it equaled, what kind of a triangle is that? It's what? It's a right triangle. If it was greater than, it was what? Obtuse, good. And then if it was less than, by a process of elimination, it would be. Again, the only thing that was weird with those is sometimes they gave you all those different square roots, and you weren't sure which one was which. So you always check the decimal equivalencies to tell which one it is. Okay. You guys are writing that out. Let me pull up an example of that real fast. I'll bring it right back. I'll show you.